In this lesson, we're going to talk about Snell's law and critical angles. So anytime we have light that goes between two different mediums, things happen to it. So if I have an incident ray, that's the light that comes in and it hits a piece of glass, some of the light is going to get reflected back. So if it's going from an air as a medium to the glass medium, some of the light gets reflected, and some of the light goes into the glass and gets refracted. Refracted means it goes from one medium to another. When it goes from the glass to the air again, some of that light again will get reflected and some of it will get refracted out of the glass. And you'll notice that the angle of the light has changed as it's gone from one medium to the other. So refraction has to do with how light changes when it goes from one material to another. The equation on your AP Physics 2 equation sheet for the index of refraction is N equals C over V. N is the index of refraction of the material. Indexes of refraction start at 1. That will be the index of refraction for a medium. And then all other materials are greater than 1. So air is very close to 1, water is greater than that, diamond is 1.5, or glass is 1.5, diamond is 2.42. You don't need to learn indexes of refraction. You should know that a vacuum is 1. The C in the equation is for the speed of light, which is 3 times 10 to the 8th meters per second. That's on your equation sheet. And the V is the velocity of the light in the material, because when a light goes into a new material, it doesn't travel at the same speed. So the speed of light in a vacuum, 3 times 10 to the 8th meters per second, will be in the equation, and then the speed in the new material will be on the bottom of the equation. So let's do a problem. Let's say light travels through a vacuum, and we're actually going to be a little more precise. Travels at a speed of 2.998 times 10 to the 8th meters per second. Determine the speed of light in water, given that the index of refraction of water is 1.333. So we set up our equation. We know N and we know C, and we're going to find V. So we put in our value for N, which is 1.33, our value for the speed of light in a vacuum, and we're going to rearrange it and solve for V, and we get that the speed of light in water is 2.249 times 10 to the 8th meters per second. This is less than the speed of light in a vacuum, which is what we expect, and that's your answer. We're going to talk about what happens in terms of angles when light hits different surfaces. You can see in this picture we have light all traveling at the same angle. These are parallel beams of light, and they refract at the same angle once they hit the new medium. But oftentimes the light's going to come from a point source, and in that case it hits the surface at different angles and then refracts at different angles. So how do we figure out what that angle is going to be for each beam of light? Well, our incident ray comes in and hits the surface, and we measure an angle from the incident ray to the normal. The normal is perpendicular to the surface. The angle between the normal and the incident ray is our angle of incidence. We call that theta 1. Then inside the material, we have another normal, that's an internal normal, and then our refracted ray is measured from the normal to the refracted ray, that's theta 2. That's our angle of refraction. So we have medium 2 and medium 1. In this case, medium 2 has a greater index of refraction than medium 1. The equation that you're going to use is Snell's law. This defines the relationship between the angles and the indexes of refraction, and it is n1 sine theta 1 equals n2 sine theta 2. This is on your equation sheet. n1 is the index of refraction of the first medium, n2 is the index of refraction of the second medium. Theta 1 is the angle of incidence, and theta 2 is the angle of refraction. You'll notice that when we change mediums, if we go from when we go into a larger index of refraction, so as we go from this one to a material with a larger index of refraction, from medium 1 to medium 2, we end up with a smaller angle. And likewise, if I had light that was going from medium 2 to medium 1, the angle would get bigger. That's the relationship that you will see. So let's do another problem. Let's say a ray of light travels through air, which has an index of refraction of 1, approaching the boundary with water, which has an index of refraction of 1.33. The angle of incidence is 45 degrees. What is the angle of refraction? We're going to use degrees for these problems. So we plug our values known into the equation and solve for theta, and we get that the angle is 32.1 degrees. So we were going from a small index of refraction to a high index of refraction. That means we expect our angle to decrease, and it did. We also have certain angles at which things start to reflect completely. So this is called the critical angle, and you can look at this diagram. If the angle of incidence, let's say it starts from 0, if we hit a surface with an angle of 0, if you plugged it into Snell's law, you'd find that the angle of refraction is also going to be 0. So we increase the angle, so now it's at 15 degrees, now it's at 30 degrees, now it's at 45 degrees, and there's going to be some angle, and each material is going to be different where that critical angle is. But as we reach a certain angle, we notice that our reflected light, you can see here, is getting stronger and stronger, and our refracted light is getting less and less. And eventually we reach an angle which is unique for each material. We reach an angle where all the light is reflected and none is refracted. This is called our critical angle. This is the minimum angle between two mediums where there will be total internal reflection of the light. All the light is reflected, none is refracted. So things that have to happen for total internal reflection, the light has to be in the more dense medium. So we can't go from air to glass and have total internal reflection. It has to be going from glass to air, or from the medium with the greater index of refraction. The angle of incidence has to be greater than the critical angle or equal to the critical angle. That's the point at which we will have total internal reflection.